Okay, our next speaker is Dr. Kelly Backus, and she is coming to us from MITRE. She's the lead quantum physicist, and she's going to be speaking to us about quantum sensors for complementary PNT, position, navigation, and timing, and resilient communications. Dr. Backus, please say a few words about yourself as well.
Hi, I'm Kelly Backus. I'm from the MITRE Corporation. We're based in McLean, Virginia. And this talk, rather than focusing on specifically what we're up to in the quantum space, I'll try to highlight that as it's relevant. This is meant to be more of an overview of quantum sensors for complementary PNT, which has been very relevant to this conference, as well as some particularly promising technologies in the resilient communication space. And I've been fighting a lingering cough for a few weeks now, so please bear with me as I take about 100 water breaks in order to get through this presentation. Oh yeah, I'm prepared. Um, so kind of starting off with the basics, what are quantum sensors? The definition for this talk are going to be purposefully vague, and I've been at conferences where people have spent hours arguing about exactly what a quantum sensor is. We're not going to take the strict definition that some people take, and here I'm just going to define quantum sensors as devices that exploit quantum phenomena in order to measure physical quantities. So here, again, purposefully vague. And under that definition are a number of sensors starting at atomic clocks, which you might go, wow, that is a very loose definition of a quantum sensor. That's counting time, that's not even sensing. But people do tend to lump atomic clocks into this broad quantum sensor category. And so for completeness, we are including that here as well. Also, we'll be discussing inertial sensors, gravimeters, magnetometers, electric field sensors, and photonic sensors, which you might argue are just electric field sensors in the quantized sense, but we'll break them out separately. And again, all of these sensors kind of go into this complementary PNT space. And then these sensors up at the upper end cover this resilient communication space as well. And then here at the bottom are applications outside of the two broad categories that we'll be discussing today, but are also very promising applications of quantum sensors. And if you're interested in talking about them, either feel free to interrupt me when it seems relevant, given kind of the end of the conference, light crowd, I'm happy to talk. Or afterward, flag me, and I can talk about anything that you want to. So all the quantum sensors that we saw on the previous slide have kind of a wide range of maturity. And some you can buy off the shelf. Microwave atomic clocks have been available off the shelf for decades. That's kind of the most mature of this broad umbrella of quantum sensors that I'm including here today. And then you go kind of to the very opposite end, and you have the laboratory scale quantum sensors like this kind of niche squeeze light-enabled optical interferometers. But really, most quantum sensors kind of span this range. And when people try to say this quantum sensor has a TRL X, it's really hard to pinpoint that because it's so dependent on exactly the application and the environment and everything. And so there are going to be quantum sensors like SNSPDs, for example, that you can buy off the shelf and use for some applications, but the sensors themselves are also very much in development. And so trying to define a single TRL or maturity for a sensor is very difficult. And basically what I like to say is all quantum sensors are all maturity levels. It just depends on the application. And so today's focus, quantum sensors for complementary PNT and resilient communications. We'll be kicking it off with PNT. So first, clearly this is a talk that loves definitions. What is quantum PNT? And quantum PNT is just a small subset of the wide space of complementary PNT. And complementary PNT is PNT that both aids and could be used in place of GPS in either GPS denied environments or environments where you need something just a little bit more specific or a little bit more accurate. And quantum PNT is a subset of sensors that can offer those services. And this includes quantum clocks for time holdover, or inertial navigation, which is based on kind of velocity acceleration, or position fixing techniques like magnav or gravity-based navigation. So Here is kind of an overview of the complementary PNT ecosystem as a whole. Here in the left column are sensors and technologies that are used for complementary PNT. This is probably not exhaustive, but it's meant to be representative of this space. And then here in the right column are PNT techniques that take advantage of these various sensors and technologies. And here in yellow are the quantum sensors that can, or the technologies that have a quantum version that can be used in this space. And so these include clocks, radio receivers, inertial sensors, gravimeters, and accelerometers, as well as magnetometers. And these have, as I mentioned, kind of a range of TRL. And even though I just said it's really hard to define TRLs for specific technologies, it gets a little bit easier when you say you add the technology and the use case, in this case, PNT. And so quantum atomic clocks have been used for PNT for ages. So that's going to be TRL 9. And then both GravNav and magnetometry, like that's a very well-studied field, doing gravity mapping, magnetic field mapping for navigation. And then kind of in the middle is the space of inertial sensors, and at the very low end are kind of radio receivers for PNT. And so in this talk, I'm just going to be focusing on the kind of 4 higher TRL technologies for PNT, and I'll be talking a little bit about quantum radio, like RF reception, in the communications side of the talk, but not in the PNT side. So to kind of dig down a little bit more into the 4 quantum PNT techniques that we highlighted in the last slide. The first is going to be time holdover, so maintaining precision timing and synchronization in the absence of external signals. And this is where atomic clocks really shine. The next is going to be inertial navigation, so using those changes in velocity or acceleration in order to estimate kind of where your platform is moving. These sensors aren't going to be absolute PNT sensors, but can be used in conjunction with other sensors with the correct algorithms. And here you're going to see things like accelerometers, gyroscopes really shining. And then the bottom are the position fixing technologies of magnav and gravnav, which you both are going to see these quantum sensors used for the mapping and then for the navigation that follows those maps around. So the takeaways before we go into like slightly more detail are that the quantum clocks and sensors are going to offer long-term stability and accuracy compared to their classical counterparts. For all of these technologies, that's not necessarily true right now, but that's more of a statement in the long term as these technologies continue to develop. And here at the bottom it's highlighted, magnav and gravnav are not necessarily suitable for every platform, but they're passive techniques, which makes them really useful in situations that other techniques might not work or might be a little more complicated to use. So starting with the oldest, most well-known quantum sensor, so atomic clocks. And these have been around since the 1940s. So like the question that was asked in the last couple of talks, how far along are we in implementing quantum sensors? In the case of atomic clocks, they've been around for a long time, even before they've kind of retroactively been lumped into this field of quantum sensors. But themselves, well studied, well used, well loved. And there are many different atomic clock architectures, a bunch of different ways you can build these, but generally you're going to have some classical local oscillator that's coupled to your quantum physics package, and that's going to be your atoms that have some intrinsic energy state that you're taking advantage of. And this feedback loop here keeps your classical oscillator stable by coupling it to that really set atomic level structure. And then you get your RF output, great timing. And most of the atomic clocks that are on the market today and that are in use today are microwave atomic clocks. And that means that the atomic states that you're using in this physics package kind of oscillate in the like microwave domain. And these are used all over the place today. GPS, communications, financial transactions, really the world kind of runs on microwave atomic clocks. And these exist everywhere from these tiny chip scale atomic clocks up through these hydrogen maser atomic clocks that are more, I want to say, the size of this podium here. And you get kind of spread of time stability across all of these devices. And even though these have been great and they've been in use for a long time, physicists have asked, how can we make atomic clocks even better? And it turns out that uh, the stability of your atomic clock scales with the frequency of the atomic transition that you're dealing with here. So the higher frequency atomic transition you're dealing with, the more stable your atomic clock is going to be. And so people have moved from working on microwave atomic clocks into optical atomic clocks. And so here, the atom frequency that you're working with is in the kind of like optical frequency regime rather than the microwave frequency regime. And what made that possible was the invention of optical frequency combs, which enables you to hop between kind of the RF, like classical oscillator here, and your optical atom frequency here, because before that technology existed, you couldn't make that transition for your feedback loop. It wasn't going to work. You couldn't take advantage of these higher frequency optical atomic states. And this has been so successful that the international timekeepers are moving the definition of the second from cesium-based microwave atomic clocks, which is what defines the second now, to optical atomic clocks in the near future. And there have been recent efforts to kind of get these into the commercial world so you can buy them off the shelf. And there are two examples down here, filament inflection and vector atomic. And these are, yeah, like 3U rack size units that can provide this atomic clock, optical atomic clock level stability. And so I gave a little bit of the outlook on atomic clock technologies in the last slide, but here we have the kind of performance of these atomic clocks plotted alongside your size. And here, better is down, so the more stable, the lower down on the figure. And so you can see these kind of interesting things where you're looking here like, okay, you have these emerging classical sensors that look like they're competing in stability with atomic clocks, but what I want to highlight here is that this is short-term stability, and there hasn't been a lot of research done to show what the long-term kind of like long time holdover of kind of this technology specifically is going to be. And so you see these emerging optical atomic clocks down here, very far on the bottom of the plot. So they're very stable. They're still quite a bit larger than your microwave atomic clocks, but people are working on them. They're starting to miniaturize, and it'll be interesting to see where those go. So next, we're moving into quantum inertial sensors. And with quantum inertial sensors, what you're doing, like a normal inertial sensor, you're using the information on changes of velocity or acceleration of your platform in order to keep track of where your platform is going. And there are kind of two primary quantum inertial sensors that people generally talk about. And the first of these atom interferometer-based accelerometers and gyroscopes, and the other are NMR-based gyroscopes. So those are just kind of two different technologies that do a relatively similar thing, can have slightly different performances, slightly different swap packages. And then those are going to be situated here. So the NMR gyroscope, while very small, doesn't have the world-class stability. And again, here we're looking at down is better. I like to highlight that because in a lot of plots, more is better, not in this talk, unless I change that later, which I might. And then you look over here at these laboratory scale atom interferometers and gyroscopes, and they offer a lot of sensitivity. And while this isn't giving you the exact size, there have been very promising demonstrations that show that in the near future, we might be able to get better performance out of these quantum inertial sensors over traditional sensors. Then moving into quantum gravimeters. Here, I've also highlighted two primary technology areas for quantum gravimeters. One of them is going to look very familiar to the last slide, which are, again, these atom-based interferometers, because what is measuring gravity other than just measuring a very specific form of acceleration? So you end up using very similar technology for that, just kind of designed a little bit differently, tweaked specifically to measure gravitational acceleration. And then the second one highlighted here are superconducting gravimeters and gravity gradiometers. And these are kind of wacky devices where you have a supercooled kind of hunk of metal, like magnetically levitated, which becomes very sensitive to changes in your local gravitational field. While very interesting, these haven't been deployed, shocking, haven't been deployed quite as widely as these atom-based interferometers, which you'll see in these kind of recent development and trends have kind of been used all over the place, both kind of where this is very much a research scale example where the University of Birmingham in the UK did a demonstration where they got all of their equipment that it takes to create one of these atom interferometers into a cart around this size, and rolled it around the university parking lot to map out I want to say, yeah, 20-centimeter tunnel that was under the parking lot to pretty high accuracy. And what was novel about this, it was a couple years ago now, was the system itself was light enough and portable enough that they could do this mapping in, I want to say, an hour. So they kind of took it, mapped one spot, went to the next, and it was both fast enough and light enough that just this research team could do it. Because often when you see this equipment, you're like, I can't lift that, that's too heavy. That's going to take some time to resituate it to make your entire map. This showed that you can make it light enough that you could do it in a more reasonable way and in a more reasonable time. And these atomic gravimeters have also been deployed for volcanic monitoring. So you can do like seismic measurements similarly in interesting ways. And then there's also been these tests of vector atomic gravimeters over here. And as well as gravitational navigation, these are also going to be very useful for subsurface mapping, which we mentioned here, and mineral exploration and other kind of geophysical phenomenon. So then, taking one of my million water breaks. So the last technology I'm going to highlight in the kind of quantum sensors for PNT are quantum magnetometers for MagNav. I'd say atomic clocks are kind of far and away the most well-studied, most well-known quantum sensor for PNT, but magnetometers are, I don't know, probably the distant second, probably the next thing people really think about when they think of quantum PNT. And here there are two technologies cited, both these atomic vapor magnetometers, which you can just buy off the shelf, as well as these solid state defect magnetometers. You can also use squid-based magnetometers for this, but they're not highlighted on this slide. And quantum magnetometers are both well studied in the mapping sense and in the then the navigation sense. And so some recent trends are you're just seeing this widespread of atomic magnetometers from numerous vendors. You got Geometrics, QSpin, TwinLeaf has really good ones. And you're starting to see this magnetic navigation, people working on putting it into place and testing the limits of it. And so here you see that people were able to achieve sub 20-meter position accuracy in around an hour. And some key advantages of this are you're going to have comparable size with really fantastic sensitivities. And that sensitivity is going to be key both for the mapping, because the more sensitive you are, the faster you can do that mapping, and then for the navigation with that mapping later on. And these have good long-term stability and accuracy. And here you can see again, called out, they're quite small. At least these guys are around the size of coins. So one last slide on position fixing with quantum sensors. So this is highlighting the last two sensors I talked about, these magnetic sensors and the gravitational sensors. And while you see here, there are a number of different ways to do accurate positioning. And both gravity navigation and magnetic navigation aren't really like killing it in the position accuracy sense. There are reasons you're going to want to use them that aren't just specifically for knowing most accurately where you are. There are three key advantages here. The first is that these are passive techniques. You're just sensing, you're not using LiDAR, radar, sonar, doing sending and receiving to figure out where you are based on any kind of uh, landmark. They're very difficult to jam. No one's running around with giant gravitational forces trying to trick you about where you're going. Um, and then the last is that they can operate in all weather conditions and all times of day, unlike image-based or celestial navigation techniques. And so these are generally the pros of MagNav and GravNav, but there are also specific value to using quantum sensors for these two navigation techniques. The first is that they're likely to be better for generating high accuracy maps. And while I wish I had a graph that would highlight exactly why that's true, I'm going to ask you to trust me. We can talk about it if we need to. And then the second is that once maps are generated, quantum sensors can then be used for the navigation themselves due to the long-term accuracy and stability. So now we're moving into quantum sensors for resilient communications. And what I want to emphasize here before we go into the actual slides on this is we're not talking about quantum communications. This is another place where people will argue day in, day out about what, they're like, this isn't quantum communications because you're not dealing with entanglement. It's like, yeah, it's okay. It's just classical communications enabled by quantum sensors. So we're not thinking quantum communication here. We're thinking traditional communications with a quantum-based receiver that's going to give you kind of interesting or different properties than you would get from a traditional receiver. And so here's kind of the broad space of various quantum sensors that can be used for resilient RF and optical communications. So first, you can do communications with squid magnetometers, which spans this huge range. And then next, you're going to see Rydberg atom electric field sensors. These often kind of come in similar conversations. I'll talk a little bit about why those two techniques are going to give you a little bit different, like kind of the pros and cons of those two sensors. And then the next are atomic magnetometers, which, while good for PNTs I just talked about, you can also do similar communications with those. And then here, NV diamond magnetometers, and I won't specifically be talking about those sensors for communications, but I'll kind of highlight them for a kind of left field application compared to the rest of the talk in one of the last slides. And then here on the other end, we have SNSPDs for resilient optical communications. So SNSPDs are single photon detectors that work from the visible down into the kind of increasingly far IR. Researchers are kind of doing some really interesting work expanding their range. I'll talk a little bit about that. So specifically, I'll be giving you a slide overview of Rydberg atom electric field sensors, squid magnetometers for communication, and superconducting nanowire single photon detectors. And then, as I mentioned, I'm going to highlight a little bit at the end some MITRE R&D in Rydberg atom electric field sensors and NV diamond magnetometers, not for PNT or communications, but for microelectronics assurance. So the first sensor I want to talk about is Rydberg atom electric field sensors. And the idea here is you have this little kind of cell of vaporized atoms. So people traditionally use either rubidium atoms or cesium atoms. And then depending on the type of atoms you're using and the states that you want to access in those atoms, you propagate various lasers through that cell of vaporized atoms. And you're exciting the atoms in the laser path to very high energy Rydberg states. And what you're doing there is you're pulling the negatively charged outermost electron very far away from your positively charged nucleus, creating thousands of tiny little dipoles within your cell of atoms. And each of those little dipoles becomes very sensitive to incoming electric fields. And because you're not dealing with a physical resonance the same way you would with a traditional dipole antenna or other traditional antennas, the incoming frequency that you're most sensitive to then doesn't scale with the size of your sensor. You're using the atomic resonances rather than a physical resonance, so you can do sensing all the way from near DC up through hundreds of gigahertz with your same sensor head just by changing the frequency of the lasers you're using to excite your atoms, which changes the state that you're doing your sensing with. And so that gives you a few key advantages. You end up with a really small size sensor head and broad tunability, not from DC to terahertz, but from near DC to hundreds of gigahertz. And one misconception people often have about Rydberg sensing is that this means that you can do really broadband sensing. And I want to highlight here that while you can do broad tunability, what you really get is a very narrow band sensing window that you can tune across the whole spectrum. And this small sensor head that doesn't scale with what you're actually sensing and this broad tunability gives you really good enhanced spectrum situational awareness. And particularly in the communications environment, you can do really agile communications across your spectrum with one device. And a few recent developments and trends. So these have been done kind of by experts across the field. So there's sensor head miniaturization. So this is just a little wand of atoms. It's about this big. People are working on angle of arrival measurements. And so you can imagine it'd be nice to be able to do angle of arrival work with a sensor head that big. And then also kind of standard waveform detection, like AM, FM, like PSK, everything. One kind of funny thing about electric field sensors where this is kind of an active state of research, or like how to receive all signals, is that the interaction between your lasers and your atoms does the signal demodulation for you. Unlike a traditional antenna where you have signal, goes to antenna, and then goes to your back end where your SDR, you tell your SDR, I want to demodulate this signal, this is the modulation scheme. It happens in that initial interaction depending on how you do your laser locking. And so you have to make sure you're set up in such a way that you're going to demodulate properly. And people have done a really good job showing that you can, in fact, do proper demodulation of the vast majority of popular waveforms. You just have to think there's that extra step of making sure that you're doing it properly, and you can't just rely on the same algorithms that you've used for all other forms of communication. So that kind of goes into this last point here, which is that these sensors can be thought of not as just a device that replaces the antenna of your system, but it's the antenna and that like front end demodulation part of your electronics, which depending on who you ask is a pro or a con, but I think it has some interesting implications that people are studying. Then the second technology that I want to focus on today is squid magnetometers and squid arrays for RF sensing. And like Rydberg atom sensors, you're using an array of quantum states in order to sense traditional RF. And here, instead of atoms and lasers, you're using superconductors and supercooling in order to access your atomic states. And also similarly to Rydberg atoms, you are going to aim for a swap advantage at specific wavelengths. And the key difference between the Rydberg sensors and squid array technology is that rather than broadband or kind of wide tunable bandwidth that you can kind of go between with your narrow bandwidth, here you're looking at more broadband devices.
What's the frequency range?
The frequency range, theoretically, you're just going to be limited by your superconducting band gaps. So that's kind of goes up into these higher ranges.
And the bandwidth, do you know?
I don't want to cite numbers for a lot of the technologies.
Sure, of course, thanks.
So, yeah, let's see, where are we going from here? Okay. So I accidentally skipped the how does this work and just went into the bandwidth argument on this technology. So we're going to rewind a little bit. So what you have with squid magnetometers, and traditionally when you're using a squid magnetometer for kind of other squid-based technologies, is these tiny superconducting loops with a gap of superconductivity that gives you a quantized response to your incoming magnetic field. And when you have just one squid or an array of identical squids, like you would use in a lot of magnetometry, you're going to end up with a nonlinear response. But if you instead make this kind of wacky array of, sorry, my throat's getting to me on this slide a little bit. You can instead make an array of squids that's going to give you that more wideband, more linear response. And the experts in the field are working on things like swap reduction, improved circuit design, and kind of characterizing some RF measurements. And then the next technology I want to talk about are superconducting nanowire single photon detectors, or SNSPDs. So here we're hopping from kind of the RF quantum enhanced communications into the optical quantum enhanced communications. And SNSPDs are similar to squids, kind of tiny, like microelectronic chips with superconductor fabbed on it. And depending on how you fabricate your superconductor in the squid sense, you're making these little loops, and those are sensing your magnetic fields. In the SNSPD case, you're fabricating this little like superconducting meander. So think of it as a snake of a superconducting material that's very narrow. And when you have a photon come in and hit that little snake, it's going to break the superconductivity and put a voltage onto your readout, which you can then detect. And these are really cool. They can detect single photons with really high efficiency, really low dark count rate, and these can be fabricated to sense wavelengths from the kind of, they traditionally have worked in the visible range, the word I was looking for, and people are pushing them into the near and the far IR. So the longer wavelength you go, the lower energy your photons are going to be, and the harder it is for those like weak, low energy photons to break your superconductivity. So you have to start kind of making these SNSPDs out of really weird materials, kind of bad superconductors, in order for that superconductivity to be broken by those kind of weak little photons. And so that's the R&D that I'm highlighting down here, which is creating these kind of mid-infrared SNSPDs that go all the way down to 10 micron, and recent results have shown out to 30, and they think they can push it out to 100 micron. And that work is being led by NASA JPL and collaborators, mostly with the goal of doing exoplanet detection, so not communications, but we think that, you know, if you're looking at these exoplanets trying to figure out what interesting chemical signatures are coming from them, you can then also do interesting chemical sensing on Earth. And then on the communication side, you can use arrays of SNSPDs rather than a single SNSPD to enable extremely high count rates that you can then use for optical communications. And because these are, you know, as the name might suggest, single photon detectors, these will enable optical communications in very difficult environments. So NASA, again, is pioneering the use of these for deep space optical communications, where if you're starting your communication in deep space, by the time your photons hit Earth, there aren't many left of them in order to collect. So you need these really, really sensitive detectors that are going to pick up the last photons left of your signal. There's also interesting work being done to do kind of optical communications through fog or other kind of like photon-starved media. Generally, is the word people use to describe the environments where SNSPDs are going to give you an advantage in the communication sense. And that's just SNSPDs for what we call like quantum enhanced communications. SNSPDs are also generally the detector that people are going to use in traditional QKD or quantum communications. That's just not the focus of this talk. And SNSPDs are generally or always fabricated out of low temperature superconductors nowadays, People are working on fabricating them out of like higher temperature superconductors, but it's very difficult to break the superconductivity of a higher temperature superconductor with a single photon. So we're kind of stuck in this low temperature world with SNSPDs. And traditionally that's gonna mean, as we heard in the last talk, a cryostat kind of around this size. But there are cryogenic companies that are trying to make them more compact and more usable. And so here's an example of a cryostat. It doesn't include all, like there's a key piece of supporting equipment that's not included in this photo, but you are starting to see these much smaller cryostats even for 4 Kelvin systems. So now we've hit the end of kind of the overview of quantum sensors for complementary PNT and like quantum enabled or enhanced communications. And we're gonna hit the point where I'm gonna do a little bit of highlighting of what MITRE itself is actually up to. So we like to show this graphic of kind of what all those quantum sensors are. So you can do magnetic field sensing, photonic sensing, time, frequency, gravity, inertial electric fields, all the stuff that we've talked about today. And the places that MITRE have traditionally done work are in this solid state defect magnetometer space, so NV diamond magnetometry, and in Rydberg atom electric field sensors. And we've also done a lot of work supporting atomic clock, atomic gravimeters, kind of everything you see here in yellow. This work is more in the future projection or the modeling space. And then we're working on starting and eventually growing a work program in superconducting sensors because we believe that this is kind of an understudied part of quantum sensing in the government space. And so me and one other employee have been spearheading that. And so this is going to be looking at superconducting magnetometers and SNSPDs, which is where we're really trying to kick that off this year. So then the 2 experimental efforts that we currently have, again, hoping to grow this in the near future. The quantum sensing group is in itself still relatively young. The first half is the Rydberg atom electric field sensor. So the lab for this work has been around for about 5 years now. And I've already talked quite a bit about Rydberg atom electric field sensors, so I won't kind of belabor this point too much. But here's a photo of our sensor head. We work in close collaboration with ARL, and they 3D printed that cell holder for us. You can see ARL there. And what we're really working on there is this kind of broad spectrum situational awareness for electronic support. And what's not highlighted on this slide is work that we're doing in order to do some ruggedization of Rydberg atom electric field sensors. So we've done some testing, kind of trying to get this out of the lab, trying to get this kind of off that big, heavy optical table that you're never going to be able to move around or put in the field. So this Rydberg atom electric field sensing work, yeah, both working on this broad spectrum support and actually trying to help ruggedize the system, because getting lasers to work outside is not easy, but it's possible, and we're hoping that we can do it. And then the next side of this is the quantum diamond microscope. And so this is a magnetometer that uses nitrogen vacancy centers in diamond in order to do magnetic field sensing. And one really interesting thing about the QDM, as opposed to certain other quantum or even regular magnetometers, is you get inherent vector imaging from it. So by putting this diamond on top of whatever you're trying to sense, you can actually see the map of magnetic field from that single sensor. And what folks at MITRE are working on is using this for microelectronics assurance. And by looking at the magnetic field, you can actually map current kind of making its way through a chip and starting to make some intelligent guesses about what that chip is up to, what it should be up to. And so here are just some photos of the QDM lab and of the Realm lab, which is the Rydberg lab. So here's the last slide, and we're kind of going to go move away from the specifics of what we're up to back into the outlook for quantum sensor R&D and highlighting these 2 key challenges. The first is miniaturization and ruggedization, and here you're dealing with photonic integration, laser miniaturization, which is a big hurdle kind of fabrication. These NB diamonds are great, but the diamond supply is a really big problem, something we both take very seriously and joke about a lot because complaining that you can't get enough diamonds sounds like you're all burglars. um,
Right.
we were visiting collaborators at ARL, and one of their labs had lost a diamond down the drain, and they had grad students spending hours trying to find it because you don't want to lose your diamond. Um, and the last one is improved cryogenic systems. And don't necessarily agree with this last bullet point here. What we really are working on is trying to like motivate the miniaturization of higher or lower temperature cryogenic systems. There are existing high temperature cryogenic systems that are quite small and quite rugged, whereas the kind of like 4K systems really they can shrink, they should shrink, and we want people to shrink them so that you can use things like SNSPDs in more environments. And then the second key challenge is just kind of connecting end users with the people doing this quantum sensing research because you never want to have a solution that's looking for a problem because then you're going to end up solving stuff that doesn't need to be solved. Instead, you want to find technology gaps, sensing gaps, capability gaps, and then look at the suite of tools and say, okay, what can we as quantum sensing researchers bring to help you fill those gaps? And so conferences like this are very important for helping engage with those communities and trying to build those gaps. So that's everything I have. Thank you for listening.
Fascinating. Thank you, Dr. Backus. Questions in the audience? Yeah, Virginia, please. Can you step to the microphone?
Honest to God, I would really like to know if you use R&D dollars to buy diamonds.
Yeah.
Now, what color of money would you use? Honest.
They're not as expensive as jewelry diamonds. They're both smaller, and you're just dealing with kind of a different. So I'm not quite the expert on this. My colleagues who work in NB diamond magnetometry would know more. But the kind of interesting and annoying thing about working in NB diamond research is I forget the name of the company that sells most NB diamonds. It has the same parent company as the company that monopolizes jewelry diamonds. So you're dealing with the same limited pipeline, and there are groups at places like MIT that are working on creating diamond fabs specifically for scientific applications to kind of break that monopoly, but it is kind of an absurd and like humorous situation. Yeah. Yes. Yeah, so the reason jewelry diamond folks actually end up being really good at manufacturing scientific diamond is in jewelry diamond, you want your diamond to have no imperfections. In scientific diamond, you need to have you want it to have specific imperfections because those are what enable the sensing. And so the people that are really good at taking out the imperfections are also really good at putting them in precise ways.
My old ex over here. You mentioned mapping, gravity and magnetic mapping. Do those maps exist? How practical are they to produce? And do you need access to the area? Like, can you do it from space, or do you need a vehicle driving around somewhere?
Yeah, so I am not an expert on the mapping process itself, but one reason people are interested in quantum sensors for the mapping process itself is that the more sensitive your like mapping sensor is, the longer standoff you can use in order to make that map. And so it's easier to do something from space, say, because if you have some constellation that you could in theory use, that's great because you're going around the world all the time. But a lot of traditional sensors, you're kind of I don't know what you call it, the grading that you're going to get is limited the higher you go. even with quantum sensors, the higher you are, the less resolution you're going to get. But there are games you can play there. Right now, I think most of the mapping is done aerially.
Okay. And I know the magnetic fields drift relatively quickly, so you would need to redo these maps all the time, or?
Yeah.
Okay. Thank you.
This is the last presentation of the day, so no more questions? These are really, I mean, these were fascinating presentations. Please, Dr. Pazinski.
Hi. So for the Rydbergs and the Rydberg cell, how large does it have to be? So is there, so there's probably an ideal size that you're working with. So that's I have 3 questions. So
Yeah.
that's the first one.
Yeah. So this Rydberg cell, so this is the one that we have in the lab at MITRE, is about this big, and it's either, I think it's root N scaling, so the more atoms you have, the more sensitive you're going to be to a point. And so people like to say that you could make this smaller and smaller and smaller, but the smaller you make the cell, the less atoms you have. You have this atom sensitivity trade-off. And so in practice, you just need a few atoms, but there is that classic trade-off.
Yeah, because I was going to ask if you can put it at the chip scale, but here's my answer, right? So
yeah, there are researchers that say that within a few years, like everything that goes into a Rydberg sensor except for the blue laser is already present in a chip scale atomic clock. There's a red laser, there are optics, there's a vapor cell. And so in theory, if you could miniaturize the blue laser, which is really hard, and even the existence of blue lasers just got the Nobel Prize a few years ago. So
what wavelength?
480.
I used to use 488. You were able to get, I think, just a diode, but if it's a slightly different wavelength, you may not be able, because it's
at least for rubidium, you're using kind of a weird wavelength, and in order to get, it might be a power question also, because you need a ton of power to run to excite the atoms that you need to excite. And so the laser that we, for example, have in the lab is like the size of a pizza box, because you have to frequency double to get into the blue to get enough power in it.
so it would be a power thing.
Yep.
Cool. So then another question is for the Rydbergs, which vice squids, where squids appear to do better at lower frequencies. Do you happen to have insight as to why?
So the squid sensors are going to like very much outperform Rydbergs at lower frequencies because the Rydberg states that you're accessing to do this sensing tend to be, I don't have the plot that I want in this talk. Often when I give these talks, I have a slide that shows kind of where Rydberg experimental results have been done kind of on the spectrum from DC up to hundreds of gigahertz. And most of the results are done in the like gigahertz, tens of gigahertz, because that's where those atomic resonances are. And so you can really only do resonance sensing for Rydberg sensors from, I'm not going to remember the exact lower limit, but gigahertz and up. And so when you go to do low frequency sensing, you're doing off resonance sensing with Rydberg sensors. And so you get a big drop off in sensitivity. I'm glad you asked that, because that's a key thing in the Rydberg sensors.
Thank you.
Wow. I don't know about you guys. I'm just loving this. I mean, it's truly. It's a fascinating topic. I'm glad that we were able to present this today. And I want to thank our speakers. 3 female PhDs. When's the last time you saw that happening? And you know that, please, that was just yes. I'm floored. The discussions were fantastic, and I would love to get a picture of the 3 of you up here, if you don't mind, Dr. Hale. If you don't mind, come on up here and we'll get a picture. And everybody, yes, I also would like to invite you to our May conference, because I'd love to hear more about this. 12 to 15 May. Come on up, please. Let's get a quick picture, and then we listen. Dr. Backus, fascinating, great stuff. Please, right up here. And then if we can, again, if you can make it out in November, right, well, let's do it in front of the San Diego thing. I might post it on LinkedIn if it's okay. This is... Thank you very much. And thanks for your presentations today and your patience and the support. I'll be in touch and invite you to the May conference out in Norfolk, Virginia. Beautiful, lovely Norfolk, Virginia, May 12 to 15. Thank you so much. Everybody else, thanks for your presence. I think our last speaker has dropped out, so this will be the final presentation for the day. Thank you for coming and staying.
Yeah, good. Good to see you too.